All right, well, we're on to our last video for Chapter 21, and this is going to be sections 7, 8, and 9 in Chapter 21. Section 7 is about nuclear fission. And so let's take a look at some nuclear fission reaction. So this is the nuclear fission reaction of uranium, and this is just one of many nuclear fission processes that can occur. When a neutron hits the uranium, we end up getting two smaller particles plus two neutrons and gamma radiation. These are the masses, and we know how to calculate, based on this, the change in mass. So our change in mass would be products minus reactants. That gives us negative 0.19913 grams. Convert that to kilograms, and then we put that into Einstein's equation, and we will get the change in energy. So with that change in energy of negative 1.7897 times 10 to the 13 joules, we'll find that that is roughly equivalent to 15 million Snickers candy bars of energy. So if you want to try to consume that much energy, I recommend not doing that. That would be very dangerous. Although delicious for the first few candy bars, the last 14,999,990 of those candy bars would probably make you very, very sick. If we were to look at the equivalent for TNT, so how much explosive would that be? It's about 4,300 tons of TNT, or 4.3 kilotons of TNT. It'd be about 560 tons of coal if we burned that coal and used that. 144,000 gallons of gasoline, approximately the kinetic energy of one International Space Station, give or take. And then my favorite unit of energy, which is the Randy Johnson fastball. And just as a reminder, a Randy Johnson fastball is worth about 149 joules. All right, so this, just using 235 grams of that uranium, produces enormous amounts of energy. Well, how do we go about using that kind of energy? And so we've got two applications for nuclear fission that are popular. One is to make nuclear reactors and generate electricity. This is a picture of the Comanche Peak Nuclear Power Plant down in Glen Rose, Texas, not very far from the Dallas-Fort Worth region. And it produces a significant amount of the electricity here in Texas. 2.4 gigawatt of electricity equivalent. So a pretty significant provider of electricity. Over here on the right, I've got the Little Boy nuclear bomb. It's a uranium bomb that was used in 1945. It was the first nuclear weapon ever used in warfare. Had a 16 kiloton TNT equivalent and had a tremendously horrible toll on life. So one bomb, and a lot of people died. Well, we're going to stay away from talking about nuclear bombs, and we're going to go back to the nuclear power plant, how it is used to generate electricity. I want to compare that to carbon-based sources, and I'll start with coal. So if we compare our Comanche Peak nuclear power plant that has the 2.4 gigawatt of electricity, that gives out, it does have some emissions because there's some backup facilities that generate electricity when the nuclear power plant isn't running. And 300 to 400,000 kilotons of carbon dioxide are emitted each year, and negligible other things. So it's a pretty efficient way to generate electricity. Compare that to the coal-fired power plant in Martin Lake. So it's on the Martin Lake near Tatum, Texas. That's not far from Longview, Texas, out in East Texas near the Louisiana border. It generates about 21 million tons of carbon dioxide. 77,000 tons of sulfur dioxide, which leads to acid rain, 15.6 thousand tons of nitrogen oxides, which leads to all kinds of other issues, and of course mercury. It doesn't seem like a lot, but trust me, 1,700 pounds of mercury is an enormous amount of mercury just to dispense into that area every year. So gives off about the same amount of energy and produces about the same amount of electricity as this nuclear power plant. If I had to pick which one I was going to live within, 20 miles of, I would pick the nuclear power plant. It is much safer to be near. When we compare nuclear power with chemical sources of producing electricity, we'll find that when we're doing chemical power, we're breaking bonds and making new bonds. Most of the time, we're looking at the oxidation of carbon. For nuclear power, we're rearranging the nuclei, we're rearranging the protons and neutrons to give us more stable nuclei. And we'll find that the amount of energy that we get out of the nuclear reactions is just enormous by comparison. So it's very attractive to use nuclear power to generate electricity. All right, that's how it's worked. And we'll find that worldwide it's between 11 and 13%, depending on which numbers you look at. 11 and 13% of worldwide electricity comes from nuclear energy. So what we want to do is we want to compare several different countries here and see where they get their electricity from and what kind of impact that has. Well, in France is the world leader in nuclear energy production. About 3/4 of their electricity comes from nuclear power, another 11% from hydroelectric. So if we look at those, 80 plus, almost 90% of their electricity comes from low polluting sources. And then the remainder is made up of some coal and gas and other things, some wind power and solar power and things like that. But they have an enormous system of producing nuclear power and generating electricity from that. And when they are not using it, they often export their excess nuclear power to other countries. The United States, we have almost 20% of our electric grid comes from nuclear power. And if we compare that to the other sources of power, gas and coal being the primary sources of generating electricity, we'll find that the nuclear has a relatively low impact on the environment compared to the coal. When we look at China's electrical pie, so to speak here, about 3/4 of it comes from coal, about 20% from hydroelectric, and then we've just got a smattering of other things, including about 5% from nuclear. China is building lots and lots of nuclear reactors, and those nuclear reactors will eventually increase the percentage and hopefully decrease this coal. If you're looking to make improvements on decreasing greenhouse gas emissions like carbon dioxide, first, get rid of coal. If you can decrease the amount of coal that is used, you will make vast improvements in your carbon footprint. And then here are the worldwide numbers just by comparison. All right, we want to look at how a nuclear chain reaction works. And I'll just go ahead and click down so we can get to the picture here. So what happens is a neutron comes in, a free neutron comes in and hits a fissionable atom. When the neutron hits it, it causes that atom to break. So it combines with it, causes it to break into smaller, usually two smaller atoms. Those two smaller atoms also give off a few neutrons. Sometimes it's 2 neutrons if it's one reaction. In this case, it's 3 neutrons. There are a whole bunch of these different reactions that can occur when we're doing uranium-235. But in the course of doing this, it releases a lot of energy. In addition to that, this one neutron, you have 1 neutron in, you get 3 neutrons out. Well, if those 3 neutrons go on and hit 3 new atoms, then you can continue this reaction on, and that is called a chain reaction. If you just get two of those to react with other atoms, so one comes in, you'll get two that will react with two atoms. Those two atoms will give off two each, and that will give us four atoms. And then those four could give 8, 16, so on and so forth. So you can have exponential growth with the number of atoms that have reacted, and it can happen very quickly. We want to look at something that's called critical mass, because you don't want the reaction to go out of control. If it goes out of control, that's a bomb. If you can get it so you maintain it at a constant level, well, that's what you can use in a nuclear reactor. If you don't get enough of the reaction occurring, you will get what we call a subcritical mass. In the subcritical mass, it will fizzle out. So our ideal condition for a nuclear reactor would be to get it up to the critical mass and maintain it at that level, and modern reactor design makes that possible and relatively safe. If it, for whatever reason, goes supercritical, as has happened in a couple of nuclear accidents, like the Chernobyl nuclear power plant accident and the Fukushima nuclear power plant accident, in those cases, the coolant goes away, and the reaction can go supercritical, and it can heat up very quickly. Of course, in a bomb, that's exactly what you want. You want that supercritical mass. So, but we're not trying to build bombs. We're trying to produce electricity. So critical mass is usually what we are looking for. Now, as far as how the reactors work, inside of the nuclear reactor, this is the main core of the nuclear reactor. There are fuel rods. Each individual fuel rod is subcritical. So each individual fuel rod is subcritical. If you take all the fuel rods that are in the reactor and put them together all at once, it's supercritical, and you've got a problem. So they put control rods in between, and those control rods will absorb some of the neutrons and prevent this from going supercritical. So you can maintain a critical mass, and if you need to increase the amount of heat so that you can increase the amount of electricity that you're producing, you can pull the control rods up a little bit, and that will increase the temperature. And if you need to slow everything down, then the control rods can come down. There are automatic systems so that if the reaction if something goes wrong, the control rods will just fall down. They will fall into their position, and that will prevent the reaction from going supercritical. Now, one problem is if there is a leak in this fluid, that leak in the fluid could cause a lack of heat transfer, and it could cause the temperatures to go up. And if the temperatures go up too much, then that could cause the fuel rods to melt. And when that happens, that is called a meltdown. A meltdown is not necessarily an explosion, but it is not a good thing. And there has been a meltdown at the 3 Mile Island nuclear power plant in 3 Mile Island. And so we'll find that that was a problem, and they have addressed how to avoid that problem. Now, in terms of, so here is our nuclear reactor, the core of the nuclear reactor. That nuclear reactor produces heat, and we've got this superheated liquid that is pushed through this pipe and pumped around. That transfers some of the heat to just some regular water. That will cause that water to boil and turn into steam. That steam can be pushed through a turbine, and that turbine can generate electricity. Well, everything from the steam over, that is how all electrical power plants work. Is you have something that creates heat, and that heat will turn the turbine. I guess the only difference would be something like a wind turbine doesn't produce heat; it just turns the turbine. And if you have a hydroelectric, then the water just rushes past and causes the turbine to turn. But for purposes of any kind of heat reactor, like a coal-fired power plant, gas, oil, any of those, they're heating up water, turning it into steam, and then taking that steam and turning it into electricity by putting it through a turbine. And then you cool off that steam and pump the cooled water back and start the cycle over. Every time you've got one of these kinds of either chemical or nuclear power plants, you have to have it near a body of water so that you can transfer heat from this steam to that body of water. So you'll always see that these things are on either a lake or a river. And that's true for both the Comanche Peak and the Martin Lake power plants that I showed you earlier. Both of those are on a body of water, and it's there to take the heat from the reactor. When it comes to nuclear waste is an issue. Every once in a while, the fuel rods become less effective, so you have to turn off the reactor, pull the fuel rods out, replace them, and then you have to do something with those spent fuel rods. Ideally, you would take those spent fuel rods, because about 90+% of the potential energy is still in there. You would take them, reprocess them, and turn them into fresh fuel rods, and then take that excess waste and put it somewhere. And so most of these are temporarily stored on the reactor site with the intent of taking them to some permanent site where they can be reprocessed and the waste could be stored long term. Unfortunately, the place where they were planning to store that waste, which is in Nevada, well, apparently the people of Nevada didn't want to have a nuclear waste facility there. And so that storage facility was closed before it was ever used. And so now we've got nuclear waste that is sitting at reactor sites. So far, that hasn't been a major problem to have those nuclear waste at the sites. It is well controlled, but in the long term, there needs to be something that is done with those. Preferably reprocessing and getting some of that energy out so they can use it again in another nuclear reactor, and then storing the leftover nuclear waste in some safe facility. So, in section 8, we want to look at nuclear fusion. And nuclear fusion is sort of the big brother of nuclear fission. With the nuclear fission, we break atoms apart. With nuclear fusion, we're going to cram the atoms together and lower the energy by doing that. Usually you'll take small things like hydrogen, helium, lithium, those kinds of things, and fuse them together. So here we've got deuterium and tritium. These are isotopes of hydrogen. If you get this up to a very, very high temperature, usually 40 to 100 million Kelvin, you can, if you get it up to that very high temperature, then you can convert it into helium and a neutron. These are the masses. Here is our change in mass. I'm not going to go through this because we've done this before. We've done this, not this exact one, but we've done one that's similar. This is, in fact, we may have done this one. I forget. In any case, yeah, we did a slightly different one on number 50 on the in-class assignment, but similar kind of results. So here, 1.6971 times 10 to the 12 joules per mole of helium is produced. If we look at that on a kilogram basis, it's negative 3.394 times 10 to the 14 joules per kilogram. So per 1 kilogram of starting material, we would have per 1 kilogram of starting material, we would generate enough electricity, or enough energy rather, to have the kinetic energy of 2.3 trillion Randy Johnson fastballs. Again, my favorite unit of energy. Well, how do we use fusion? Well, of course, you come up with a way to generate large amounts of energy, and of course, the very first thing that some people will think is, how can we blow people up? So there were scientists and engineers who came up with a way to make hydrogen bombs, which are fusion bombs. This particular bomb is called the Castle Bravo nuclear bomb, and it was tested out at the Bikini Atoll out in the middle of the Pacific Ocean. And there's quite a history behind that. I'm not going to go into the history, but it is not good, and it does not make the United States look good. But this particular fusion bomb had a yield of 15 megatons. The one that was used, the little boy that we mentioned earlier, that was used at at Hiroshima was 16 kilotons, so this one is 1,000 times more energy. So when people talk about nuclear weapons that can destroy entire cities, they are talking about hydrogen bombs. This generates 6.3 times 10 to the 16 joules, which is just a crazy amount of energy. Again, if you want to put that in Randy Johnson fastballs, that is 420 trillion Randy Johnson fastballs. Oh, before we go on to that, let's watch this video. All right. Well, I know that's not a very cheery video, but it is kind of humbling. So, all right. Well, that is the Castle Bravo. Obviously, it would be a much better idea if we could find a way to use this peacefully, and that peaceful way would be to make electricity. So there are proposed reactors that we can use to do nuclear fusion to generate electricity. And one of those proposed reactors is of this type. It's called a spherical torus reactor. This is the successor to what's called the tokamak reactor, but the idea behind it is that the temperatures needed to do fusion reactions is so high that you can't really put them into a regular container. Nothing can hold that temperature. Everything would melt. So in order to do this, you have to isolate the plasma that's generated with you have to isolate it with a strong magnetic field. So generating that strong magnetic field takes a lot of electricity. So and then hopefully you could get some electricity out by using the heat generated. Again, with this particular design, that heat out is going to be, well, it's going to be a little bit challenging. The point is that you can get those high temperatures. You can do this, but these are still very experimental, and they are a long way from producing electricity for the masses. When I was in college, they said these kinds of reactors were about 20 to 30 years away. Well, we're 20 to 30 years away, and they're still 20 to 30 years away. So we're a long way from having nuclear fusion as a practical source of energy. That said, they're going to keep studying it because the benefits would be enormous if they could come up with a workable design. All right, our last section in chapter 21, we're going to be looking at radiation in the environment and how radiation affects the human body. So we are constantly being exposed to radiation. There are small amounts of radioactive materials that are naturally occurring in the environment, and not just the ones that we have put there, but ones that are naturally occurring in the environment. We're really only concerned with the radiation that is ionizing radiation. We're not concerned with the stuff that is non-ionizing radiation. So when people say, "Oh, well, is this what kind? This is radiation you're exposed to," and you say, "Well, is it gamma radiation?" If it's gamma radiation, yes, that's ionizing radiation, something to be concerned about. But when somebody says, "Oh, well, I'm being exposed to radiation from 5G," well, that 5G is radio waves. Well, it may even go into the microwave part of the spectrum, but that is non-ionizing radiation and will not cause any lasting damage. So we'll find that since most of living tissue is water, that we're primarily concerned with the reactions that happen to water, and certain reactions can cause the bonds in water to break and form OH radicals, and those can lead to cell damage. Now, as far as the different types of radiation, how much they affect the body, we want to look at how far can these different types of radiation penetrate into the body. And so we'll find how much damage there is depends on not only how far it penetrates, what type of radioactivity it is, but also how long you're exposed to it and whether the source is inside the body or outside the body. For example, alpha radiation, when it's outside the body, is stopped by the outer layer of skin. relatively low risk. If you get that same alpha radiation inside your body, like inside your lungs or inside your internal organs, it's a whole different story, and it is very, very dangerous. Beta radiation penetrates usually a couple of centimeters into the skin, but again, if you get the elements that give off the beta radiation inside your body, that can be dangerous. Gamma radiation is from outside exposure is going to be the greatest risk because it goes right through your body and through your bones and everything, and that can potentially cause chemical reactions, which could lead to illness and death. And as I mentioned, inside the body, the alpha radiation is quite dangerous. When we look at dose, there's a couple of things we mean by dose. First, we want to talk about what the units of radiation are. So there's the gray, which is an absorption of 1 joule of energy per kilogram of tissue. Well, 1 joule of energy is not that much, and if you're exposed to 1 joule of energy per kilogram of tissue and it's infrared radiation, no big deal, you just get warm. However, if you're exposed to 1 joule of energy from gamma radiation, that could be a problem. So we've got what's called a radiation absorbed dose, a rad, and that is 1/100th of a joule, and so that means it's 1/100th of a gray. So 100 rads is equal to 1 gray. But even then, we'll find that, like I said, not all radiation is equally harmful. And so we usually take the number in rads and we multiply it by a relative biological effectiveness to weight it depending on how risky it is. The RBE for infrared radiation would be extremely low, almost zero, whereas the RBE for something like gamma radiation would be pretty high. So once we multiply that out, we'll get something that is called a REM, and a REM, let's see, 100 sieverts is equal to a REM. So a REM will tell us how much dose we're actually absorbing and how much risk we are put at. So the number of REMs is equal to the number of rads times this RBE, and that gives us a idea of how much risk we are exposed to. So when it comes to short-term exposure, so like exposure within a relatively short period of time, a day or a couple of hours or whatever, if you're exposed to 600 REMs of radiation very, very quickly, it's almost certainly fatal. An average dose within a year is about 360 millirems. So you can see, 1 rem, this is less than 1 rem. So these are the amounts of dose. If you're exposed to these quantities, you're probably not going to have a major effect. If it's 0 to 25 rems, 25 to 50, you may get sick. A decrease in white blood count. If you're already immunocompromised, that could be a big problem. 100 to 200, you're probably going to get very sick and increased risk of cancer later. 500, you're going to be in really bad shape. So we don't want to be exposed to that. So as I mentioned, a typical amount of radiation that you're exposed to in a year comes out to about 360 millirems, so less than 1 rem. And if we look at the sources of radiation, most of the sources of radiation come from natural sources, things that we can't really do anything about. So like radon, as we mentioned earlier, is about 200 millirem per year. If you happen to have it in your basement and you don't get it mitigated, that dose is going to be much higher and could lead to increased risk of lung cancer. If we come down, we've got just other sources of natural radiation, isotopes in the body. For example, potassium-40 is a naturally occurring isotope that is radioactive. And then there are the man-made sources, medical X-rays, nuclear medicine, consumer products, things that expose you to small amounts of radiation, but those smaller amounts of radiation are quite small compared to our natural sources. And that is the end of chapter 21 and the end of Chemistry 1412.